All right, thank you everyone for joining the final session of PAPL on verification. We're going to start off with Amanda Liu, who's going to tell us about optimizations for tensor programs.
Thanks. Right, so I'll be presenting on our work developing a principled, formally assured way to optimize high performance code. This type of code can be used in a lot of contexts. So, in high performance computing domains like image processing and deep learning, we're usually working with computationally intensive algorithms. And these look like complex pipelines of operations over n dimensional arrays. And when we're talking about these programs, and especially when we're optimizing them, it's important to make the distinction between what's being computed and how it's being computed. The former being what we call the algorithm, and the latter, the schedule. A schedule describes the interleaving and order of computation as well as the corresponding memory allocations. And so a given algorithm can have a lot of valid schedules. For example, consider a simple box blur algorithm which blurs an image by taking the average of the surrounding 3x3 box for each pixel by first blurring in the x direction and then the y. One way to schedule this algorithm is maybe the most intuitive way, where the computation is separated into stages, where each stage is computed and stored in full before proceeding and being used in the next stage. So the input V, shown in blue on the left, is used to compute the x direction blur, which is stored in orange, which is then used to compute the y direction blur, the output, in green. This is a common strategy in handwritten pipelines, but algorithms can be scheduled a lot of different ways with different arrangements of loop nests. So another way to schedule this same algorithm is to fuse the stages. And in doing so, no intermediary values need to be stored. So instead of computing an x direction blur and then the y direction using separate loop nests, there's now one loop nest where the average of the full 3x3 region is computed and stored in the output. This increases locality of data accesses, but introduces more redundancy and recomputation. Another possibility is we can tile the stages of computation. So instead of computing a stage in its entirety before using it in the next, different chunks or tiles can be computed at a time iteratively. And this maintains some cache locality in the computation within a tile. And also, depending on the size of the tile, there's only some redundancy in computation along the borders of a tile. And of course, by varying the sizes of these tiles across any number of stages, we can change and affect program performance. Each of these choices and knobs need to be decided on across all stages for any given algorithm. And as you can see, this scheduling procedure can get fairly complicated, even for a relatively simple pipeline like Blur. And there's a vast trade off space of schedules. And it's clear that navigating all these choices and scheduling to produce efficient code is a complicated and difficult task. However, being able to do so is critical to performance. The scheduling of an algorithm can make the difference of orders of magnitude of efficiency. So take, for instance, the performance of different schedules for the Blur program we looked at in this graph of runtimes, where the lower the runtime, the better. For comparison, Schedule 1 here represents the common handwritten schedule we saw before, where the pipeline is separated into its stages. Schedule 2 is the exact same schedule, only with the loop nest order swapped. And schedules 3 and 4 are properly optimized schedules that use a combination of different methods, including tiling. So you can see, even in this minimal case, a properly optimized schedule can result in a 40x speedup when compared to a naively written run. And moreover, a poor scheduling choice with a relatively small diff of swapping two loops can result in a 2x slowdown. So, although navigating the trade off space of schedules is difficult, it's the key to writing fast programs. One way to think of this scheduling problem is to consider all schedules for a given algorithm as a space of programs that are all functionally equivalent. In this space, schedules can be thought to be connected by rewrites that transform one into the other and maintain equivalence. Then the path between schedules becomes an equational derivation of one from the other. However, these rewrites can get complicated and brittle to write equationally when we're dealing with rewriting loop nests in imperative code. These equivalences also get a lot more difficult to reason about. And we're likely going to find ourselves working with some imperative program logics and trying to use alias analysis to convince ourselves of their equivalence. So user scheduling languages such as Halide or TVM address this issue by taking a slightly different approach. They allow users to first define the algorithm to be computed in a pure way devoid of imperative detail. So for example, this is the blur algorithm, once again expressed in Halide. And in order for this algorithm to be lowered, programmers separately specify the schedule using a series of scheduling directives to describe the interleaving of a computation. So the scheduling directives such as tile or compute at guides the lowering process. And this gives programmers great ease and expressivity in scheduling their programs without having to deal with direct reasoning about low-level code. But in doing so, optimizations are now treated as parameters on an opaque lowering process, and trying to convince ourselves of their correctness reduces to proving the correctness of the compiler that generates the low-level code. And also, this construction makes it pretty difficult to add new operations to the set of scheduling directives supported. So, in summary, trying to use an equational derivation to directly reason about rewriting imperative code can be prohibitively difficult. And the standard user scheduling approach of allowing users to specify a high-level algorithm and schedule them separately to guide the lowering process makes it easier to explore scheduling space. So one of our goals for our approach we'd like to use is a high-level functional representation for users to express programs. But more notably, we'd also like to enable users to schedule via rewrites at this same level. This would allow us to traverse the space of equivalent schedules using source-to-source rewrites that have been so difficult and impractical on imperative code more easily at a higher level of abstraction. And this framing would also better position us to get some formal guarantees for our optimizations. As we're rewriting and optimizing a schedule, we would like some formal assurances that we're in fact not changing the semantics of the algorithm and staying in the space of equivalent schedules. So in other words, we'd like for our optimizations to be formally verified, and we'll do this using the COP proof assistant. And finally, we'd like to maintain a well-defined degree of imperative control. It's nice to have a level of abstraction to protect us from having to deal directly with imperative code, but in order to produce efficient code and get all the transformations that we saw before, we still need a level of expressivity describing scheduling decisions that aren't naturally exposed at the functional level. But we'd also like to do this still without having to reason about any imperative code explicitly. So let's start by addressing our goal of functional abstraction. We introduced a pure functional tensor language called ATL, or a tensor language. And to get a little more insight into this language, we're going to take a look at a simplified explanation of the lowering of some core language constructs into C via our trusted compilation process. The tensor generation, or you can think of it as tensor comprehension construct, allows us to create tensors where each element is described by the body expression E, parametrized on some loop index I. And when lowered, this takes the form of a for loop over the index I and a final storage expression into a buffer that also stores into it at index I. The tensor sum construct sums over a range of elements described by E, and its lowering is similar except for the fact that the iterating index doesn't appear as an access in the storage access. Instead, the final statement accumulates the sum of the values. We also have the Iverson bracket taken from Ken Iverson's APL, which guards against the execution of E predicated on some condition P. And its lowering accordingly wraps the lowering of E in a conditional statement on P. Finally, the language also contains some familiar functional constructs such as let bindings. In ATL, they also bind values to a name to be referred to in a body expression. And likewise, they represent at a low level the points where memory is allocated. So this memory is zeroed out and then passed downwards in the lowering process as the destination for the lowering of another expression to write into. In this case, this is the lowering of expression E1. This format is also known as destination passing style. And so, with all these constructs, the core ATL language allows us to express the array algorithms that we're interested in. So let's take a closer look at how these constructs are used in a simple ATL program. So in this simple program, we're going to do an element-wise sum over tensors that are generated with elements that are the product of accessing tensor x at index I and tensor w at index I minus j, given that I minus j is non-negative. This is a small example of the type of code you might see generated from calculating gradients using reverse automatic differentiation. It's called a scatter because each input is going to write to multiple elements of the output. Next, we'd like to address our second goal and rewrite and optimize programs at this functional level in ATL. All rewrites are written as statements of equivalence between small ATL programs, and it's often conditional. So, for example, this theorem says that a sum over some expression that is guarded with the predicate that the iterating index I is equal to a specific value k is equivalent to that expression with k substituted for each incidence of I in E, given that k is in the original range of the sum. So this is true since the Iverson bracket has the property that if it's true, it has the value of its guarded expression, and if not, it's the additive identity. So if k is in the bounds of the sum, then when I equals k is the only index where the expression is non-zero, and so that's the value of the whole sum. And if k is out of bounds, then the entire sum is 0. This equivalence we name sum Iverson, and a whole suite of equivalences like it are proven as Cock theorems. And these theorems comprise an extensible set of transformations we can use to rewrite programs. Now, in order to get the formal guarantees for scheduling optimizations we asked for before, we need to enable users to use our rewrite theorems, preferably with minimal proof burden on themselves. So in order to actually use these theorems to rewrite and transfer programs, we also provide a powerful set of tactics in our framework. To demonstrate this, let's reschedule the small scatter example we looked at before, because scatters are often suboptimal, especially if we eventually want to exploit parallelism, since it requires each input to write to multiple elements of the output. It would be more advantageous to rephrase this as a gather, where outputs read and compute multiple inputs. And we can achieve this by essentially swapping our sum and generation loops and pushing this index offset from the axis into W onto the axis into X. So we begin by rewriting backwards using the sum-Iverson theorem we just looked at before to wrap the axis into W with a sum that zeroes out every axis into W except at index I minus j. And we do so by using this RW tactic, which takes in the name of a theorem and automates away proof details such as any preconditions the rewrite may have had. So in this case, this was the precondition for the bounds of the k. And now we want to rewrite again to allow us to push this Iverson bracket inside this sum and merge it with this other bracket so that it becomes the conjunction of the two predicates. And now taking a closer look at this resulting predicate, we see that it's true if k is equal to I minus j and if I minus j is negative. However, since k must be non-negative, given that it's within the summing range, it's clear that this statement implies the other. And we can use our simple guard tactic to automatically simplify the predicate. And now we want to rewrite to push this outer sum inwards, commuting it with the adjacent generation and sum. Next, it would be useful to get this predicate into a form of I equals something on the right-hand side, since I is the immediate index we're enclosed in. And of course, we have another tactic to take care of this. Now, finally, note that this inner sum is again in the form of a sum over an expression predicated on its iterating index equaling a specific value. So we can do a forward rewrite to collapse this expression once again and achieve the gather program we set out for. And finally, we conclude the scheduling process. So as you can see, our tactic framework allows the programmer to reschedule their program in a high-level proof script, and it reads at the level of abstract detail similar to that of a mathematical proof. So to recap, with our framework and core ATL language, we're able to express and rewrite a wide range of schedules. But if we want to schedule truly high-performance systems, our work isn't quite done. I named imperative control as one of our goals previously. But before we take a look at our approach to this, I want to elaborate a little bit more on what this means. So bear in mind that from our definition of lowering, the shape of an n-dimensional array being computed necessarily determines the loop and iteration order and index storage expressions we use to realize it, and vice versa. As it stands, this construction is really too restrictive. Consider even the simple case of tiling a 2D computation. Our lowering process of a 2D shape largely suggests a nested loop structure with a simple 2D index access pattern, solely based on the loop iteration indices. But to tile, we'll be separating the computation into several 2D tiles, creating much deeper loop nesting. And under our current construction, this would result in a 4D access pattern like so. But we still only want to realize the same 2D output. So what we really want is a special access pattern into a 2D output like so, that reflects the tiles being computed and the order that we're iterating in. So we need a high-level form of imperative control to decouple the compute order from the storage order in this way. And to do so, we introduce a set of reshape operators into ATL. These operators are actually defined in terms of core ATL constructs, and they express array operations such as concatenate and transpose. And you might notice that these operators can be grouped into pairs or left and right adjoints so that when they compose, they form the identity function. So as an example, the transpose of a transpose returns the original array. And these adjoints are just statements of equivalence in ATL, so they can be proven as Coq theorems to be further used in our rewrite framework. So to introduce reshape operators, we start with a program written in core ATL constructs. This is a small program with two nested tensor generations over expression E. The generation goes up to n and m for each respective dimension and should generate an n by m tensor. And correspondingly, the C code generated from this ATL program consists of two nested loops over I and j going up to n and m respectively. And inside these loops, we're storing into some allocated buffer for results, accessing first at index I and then j. To introduce reshape operators, we're going to rewrite using an adjoint theorem. And in this example, we are going to rewrite to introduce two transposes around the full program. And as you can see, the resulting generated code is the same. But since each operator is defined in the core language, we can unfold one of these. So we're going to unfold this inner transpose into its program definition. This results in the following program. So notice the generation operators have been swapped. The m-length generation is now on the outside and the n-length is on the inside. And likewise, the for loops have been swapped. If we ignore the remaining transpose for a moment, we would have a lowering that results in an index access pattern like the one shown here. It would be j and then I in the same order as the respective loops. However, when the transpose is left in place, it acts as a compilation directive affecting the generated code. So this transpose operator would maintain the loop nest order suggested by the ATL program, but it swaps the index accesses of the storage. And so we have effectively decoupled the compute order from the storage order by transposing the order of the two dimensions. Likewise, the rest of the reshape operators are defined to follow suit in that they can be unfolded into their core ATL definitions and further rescheduled, or they can be left intact and treated as compilation directives that induce the changes to low-level code that correspond to their function. So our reshape operators provide us a menu of different ways to decouple compute and storage order. Equipped with this, we evaluated our framework by scheduling the blur algorithm and comparing it against the same schedules produced by Halide. And as you can see, we were able to properly express these optimizations and replicate the performance. This shows that the control and expressivity you get in ATL with our framework is sufficient to match performance of a language that was designed to do this, with much weaker formal guarantees. Even more so, we found that our framework is expressive enough to enable transformations that aren't doable in Halide. This actually includes the scatter-to-gather transformation, which we saw before while demonstrating our rewrite tactics in our scheduling proof script. This is an example of a rewrite derivation in our framework of another scatter-to-gather transformation at a more realistic scale. This type of transformation is a very useful optimization pattern that's common when computing gradients in image processing programs. we're also able to express IM-to-call transformations. These were the key to allowing convolutional neural nets to exploit high-throughput GPUs. This optimization converts batched convolution operations into matrix-matrix multiplies, which could be further exploited by existing blast routines at close to peak machine utilization. And so this shows that our framework is not only able to optimize programs via high-level algebraic rewrites getting us formal assurances of correctness, it's able to produce a variety of optimizations applicable to real-world high-performance systems. Thank you.
All right, we will now take questions. Any questions from the room? No questions so far. If you have any questions, please put them up in the Q&A. All right, I'll open up the discussion with one. This seems to be like a very clean and great framework for thinking about loop transformations, but you've applied it in the context of ATL. What prevents this from being used in a general purpose formally verified compiler like CompCert for proving the correctness of many, many different kind of loop optimizations?
So I would say that the optimizations that we're concerned with right now are like very structural. So some of the optimizations that we're looking at are just from different properties like the cache locality and storage granularity. I think for other systems that would do optimizations regarding maybe certain parallelism properties or even special vectorization instructions, those aren't currently supported in our system. And I think the optimizations that you would want from a more general framework, we're able to make our system so clean because we have these assumptions on the type of things that we're going to express. So our system is a little bit more limited in that sense, but we know that this is still expressive enough and powerful enough for the domains that we're working in.
Okay, very clear answer. Thank you. We now have a question from Ralph online. Yep, there you go.
How hard is it to express the same schedule in Halide versus ATL? Is it realistic that Halide users could express schedules without having to learn Coq? So I would say that there's minimal overhead effort to be able to express a schedule in both Halide and ATL. I'd say maybe the main barrier from the Halide to ATL transitions would just be the fact that we're working with just slightly different constructs. So you're going to be working with the functional version that we presented before. But in terms of actually having to use Coq and having to learn tactics and all that stuff, we provide a fair level of abstraction, as you were able to see with our like scheduling script. So everything is performed at a high level, and pretty much all proof obligations that would require like true proof engineering have been taken away from the user. So this should be even though it's prototypical as it is right now, it's designed and it has great potential to be a really user-friendly system in that case.
All right. Well, we're right on time, so let's thank the speaker again.